Alright, in section 3.9 we're going to be talking about the calculus involved with exponential and logarithmic functions. As it turns out, the function y equals e to the x, which is already an interesting function in the first place due to the fact that its base, of course, is an irrational number, famous irrational number e. It turns out that the derivative is also equally fascinating. If we were to take a look at the graph of y equals e to the x, which we'll do now, we of course know that it's an exponential growth curve. Okay. And if we were to graph the derivative of it using our ender command, and hit graph again, notice that you don't see much. And the reason for that is because all the calculator is doing right now is redrawing the graph of y equals e to the x. As it turns out, the graph of the derivative of e to the x is itself. Okay? And it really shouldn't be terribly surprising knowing what know about derivatives and the relationship between y coordinates, because as the e to the x function is always increasing, therefore the derivative should always be positive. Okay? When we're over here, the e to the x function's derivative is very small. Okay? Almost flat, if you will. So therefore the y-coordinates of the derivative should be very close to 0, as we see. And as we move to the right, of course, the slope of the e to the x function gets infinitely big, and therefore the y-coordinates of the derivative get infinitely big. So it is a fact that when we have a derivative of e to the x, okay, its derivative is itself. Okay. In the chain rule version, it looks like this, of course. We have y equals e to the u, e to the some function, whatever it may be besides x. Then the derivative is itself times the derivative of the argument. Okay, so in words, again, that's itself times the derivative of the argument. Okay, so for instance, if we had e to the sine x, okay, we would start out by writing the derivative as itself, okay, times the derivative of the argument. The argument, of course, being sine, so therefore it would be e to the sine x times cosine x. And of course, the proper way to write that would be to put the cosine out in front. So final answer then would be cosine x times e to the sine x. Okay. Now we might ask, if e to the x is its own derivative, is that true for all exponential functions? What if I had 2 to the x or 3 to the x? And the answer is no, but it's close. Okay, the rule for a general exponential function, a to the x, okay, is the derivative is a to the x times the natural log of a. Okay. And of course in the chain rule form, it's a to the u, natural log a, times du dx. Okay? So this is yet another rule that we need to make sure that we have memorized, because when we run across an exponential function and recognize it as such, okay, we need to be able to apply the correct rule. Okay? And of course, just like our other rules that we've been learning, we also have a, besides the quotient, or besides the chain rule, of course, we still have the product rule, quotient rule to deal with as well. Okay? So we need to look for all those same patterns that we've been seeing. So let's start with this exponential function. Recognizing that it is as such, we have a constant base, we got a variable exponent. So if we were to differentiate this, we'd follow the rule that we see here, okay, which is itself times the natural log of the base times the derivative of the argument. If you think about it in words like that, it's a lot easier to apply. Okay, so therefore, there's itself, if you will, the natural log of the base. There's the derivative of the argument. Alright, and again, proper form for this would be as such: put 4x ln 5 out in front, times 5 to the 2x squared plus 4, and we'd be done. Alright, now another type of function that we've dealt with in the past is the natural log function. Okay, if I look at natural log x, okay, and I look at the derivative, and I'm going to tell you already what the answer is. The derivative of it is 1 over x. Okay, you notice that the natural log function is always increasing. Okay, its derivative is always positive. Okay, it's increasing more here. Okay, it's got steeper slopes here than it does here, so we should expect that we have bigger y values here than we do here. Okay, this is going to continue to grow, but it's going to continue to grow at a slow rate, if you will. Okay, the rate itself is going to slow to 0, which is indicated by the y-coordinates of its derivative, etc. Okay, so the general form of that then would be the natural log of u, and so therefore the derivative of the natural log would be 1 over u du dx. Okay. So, using that, let's go ahead and check out an example here. We have the natural log of x squared plus 5. That's something of the form ln u. So, in words, what I'd say to myself is 1 over the argument times the derivative of the argument. So with that said, there's our 1 over the argument part. Okay. And the derivative of the argument, of course, is 2x plus 5. So the final answer then would be 2x plus 5 over x squared plus 5x. Okay. All right. Now, if we go to a general logarithm function, some other base besides e, okay, instead of a natural log, if we have log base 10 or log base 5, whatever the case may be, okay, we also can find the derivative of those types of functions, okay, and it's related to the 1 over situation that we just saw with the ln x, okay, but ultimately the rules are as follows. If we have log base a of x, then the derivative is 1 over x ln a. Okay, the bottom, of course, the ln a is on the bottom of the fraction here. So in chain rule form, 1 over u ln a, okay, times du dx. Okay, so let's see an application, and we're going to see a couple of them after we look at these rules. So let's start with this one. We're going to go back to an exponential function, but you'll notice that the first thing you should see here is that we have a product. And if we have a product, we got to use the product rule. So therefore, I'm going to go first times the derivative of the second plus the second times the derivative of the first. Okay, minus, because of the minus here, of course. And then again, we have a product here between x and e to the x. So first times the derivative of the second. And you notice what is the derivative of the second? It's e to the x, because e to the x's derivative is itself. And then over here we have e to the x times the derivative of x, which is 1, of course. And so from here we can combine like terms if possible. If we put it in the proper form, x squared e to the x plus 2x e to the x minus x e to the x minus e to the x. And noticing that they all have an e to the x in common, play here would be to factor out an e to the x and then write it as a polynomial. And you can see that we do have like terms there if we do that. And so our final answer then would be e to the x times x squared plus x minus 1. Okay. All right, let's take a look at a couple more examples here. If I had the log base 5 of radical x. Okay, so again, knowing that log base a of x, or log base a of u, I should say, is 1 over u ln a times du dx. Okay, then my setup is going to be as such: 1 over u ln a being 5, the base. Okay, and then the derivative of radical x is 1 over 2 radical x. We've seen the derivative of that. You can write it as a power function and put it in the proper form when you get done after you do the power rule. Okay, and then of course we're going to simplify. When we get done, the two square roots can multiply by each other and give us just x, so we'd have 1 over 2x ln 5. Okay. A couple more. I'm going to look at another issue that we have here, just to make sure we're clear on the difference. In this particular case, we might look at this and think it's an exponential function, but remember, exponential functions have a constant base variable power. This is a variable base constant power, so therefore it's not an exponential function, it's a power function. So if it's a power function, we need to make sure we use the power rule. So even though this particular power is a non-rational power, if you will, it's got an irrational number in it, okay, we can still use the power rule. So there's an extended form of the power rule essentially in this section, okay, that allows us to do something like this. Okay, if I write 1 plus radical 2 x to the radical 2, because again we're going to subtract 1 from the power and we'd be down to radical 2. Now I caution you also that I see a lot of mistakes sometimes where people write 1 plus radical 2 and then times x to the radical 2 with no parentheses. Okay, this is not the same as this. Make sure you have parentheses around any binomial argument. Okay. Another example here, I have the natural log of 2 cosine x, 2 minus cosine x that is. So if I let my u be the inside function here, recognizing that natural log is the outside function, if I go 1 over u times the derivative of negative cosine, derivative of negative cosine is of course sine. Okay, and with that said, here's my 1 over the argument times the derivative of the argument. So final answer would be sine x over 2 minus cosine x. Okay, there's a couple more here. Let's look at this one. It says x ln x minus x. Recognize first that we have a product between x and ln x. So if we do product rule, first times the derivative of the second plus the second times the derivative of the first. and then minus 1 because of the other function involved. And in this case we have x times 1 over x, which is 1, ln x minus 1, 1's can cancel, so the final answer here is ln x. So this function's derivative is the natural log of x. Okay. Right. Then we want to look at one more involving a logarithm that's not a natural log. If I had 1 over log base 2 of x, I could rewrite that as log base 2 of x to the negative 1 and use the generalized power rule here, which is part of the chain rule. So if actually I did it two ways. I did it with the quotient rule first. So log base 2 of x, the bottom, times the derivative of the top, and then the top times the derivative of the bottom. I'd use my rule for the logarithm, base a, if you will, and then over that squared. Okay. And ultimately from there, this is of course 0. Okay. If I subtract here, I'm going to have negative 1 over x ln 2. Okay. And then I can simplify from there. Okay. Right. I want to look at one last part here, which is dealing with a situation that is a variable base to a variable power. We don't have a special name like exponential or power for this type of function, but it's of the form x to the x. We've got a variable base, variable power. To deal with this, we're going to do what we call logarithmic differentiation. Okay. So the process is going to be as follows. We're going to essentially treat it as an implicit differentiation problem. We're going to take the natural log of both sides, which is a valid step in any equation solving skills. And so if we take the natural log of both sides, that allows us to take the x that's in the power and put it out in front. So then our sentence reads ln y equals x ln x. And then from there we're going to implicitly differentiate with respect to x. So over on the left hand side we're going to have its natural log y, so its derivative is 1 over y dy dx. And on the right side we have a product, so x times 1 over x plus ln x times 1. First times the derivative of the second, second times the derivative of the first. And if we simplify that, we're going to have 1 over y dy dx equals 1 plus ln x. Okay. Now remember, we're still trying to find the derivative here, so if we multiply by y, we could get that dy dx alone. So if we do that, we're going to get y times 1 plus ln x. Okay. And then ultimately it would be nice, since the function was written in x from the beginning, it was y in terms of x, it would be nice to have the derivative just in x only. And if we knew x and y, we could certainly find a slope here, but if we wanted to put it in just x only, okay, what do we know about y? Well, once again, y is x to the x. So therefore, our final answer then is x to the x times 1 over, or 1 plus ln x. Okay. All right, so in your homework, you're going to be working on some problems that are similar to what we've been doing, okay, just using these new rules that we have for exponential and logarithmic functions.